a typical setup that we have in a data analysis is that first, we run our data analysis on some data that's available to us to reach some kind of decision, and then we're going to apply that decision, presumably to new data. So an example of this is the study of microcredit. So recall that microcredit represents these small loans to individuals in impoverished areas, and the hope is it's going to help bring them out of poverty. Now, there has been indeed an actual microcredit study, various microcredit randomized controlled trials. For instance, a microcredit randomized controlled trial ran in Mexico. And of course, the question is not, hey, for these particular people that were in Mexico, in these particular villages at this particular time, did microcredit help them? Really, we're hoping to apply microcredit in a future country. Maybe not even Mexico, maybe a different place in Mexico, and certainly a different time in Mexico if we were to even apply it. And so we'd like to know, can we trust that decision that microcredit, maybe helps people if we concluded that when we apply it again? And so in fact, we, I think, might worry about generalizing from our original data if it turned out that an extremely small subset of our data was instrumental to the original data analysis. And so we do find, using the methods that I'm going to talk about today, that in a study of microcredit with over 16,500 data points, a randomized controlled trial that took place in Mexico, that we can find a single data point that drives the sign of the effect. That is, if we dropped that one data point, that would be the difference between microcredit helping people and microcredit hurting people. So hopefully hearing that, you feel like, oh, it'd be really good to know what that data point is, so we could take a look at it and see what's going on. It would be really good to understand what's happening here. It'd be really good to have a check in general, to check for this kind of thing, that, if there's a very, very small portion of my data that if I dropped it would change my substantive conclusions. And the challenge that we face in practice is that it is just astronomically costly to check every single data subset, small data subset that you could drop, and then see, do I change my conclusions? And so this is where we come in. So today I'm going to talk about how we provide a fast, an automated, and accurate approximation to see what happens here, to try to find if such a subset exists. And I think what's really exciting is that while we have theory to support our approximation, the practitioner doesn't have to trust that theory because they can check conclusively whether our approximation worked at an extremely small computational cost. So in the rest of my talk today, first I'll talk a little bit more about this idea of when do we care about dropping small subsets of our data. Then I'll talk about how we would like to drop these very small subsets of our data if we had, infinite computational power. Unfortunately, we do not have such computational power. And so we're going to see that this is just way too expensive to do in practice. Even if you had tons of compute like Google or Amazon, this would just still be way too expensive. And so we're going to need some kind of approximation. So again, as I said, we're going to provide a fast and automatic approximation that can be checked at minimal cost. We're going to see that many actual real life data analyses are robust, but some are not, and this will flag it. And we're going to see that non-robustness in the way that I'm describing it today is not detectable in the usual ways. It's not just a product of gross outliers. You can't think that you're safe just because you have a small p-value. This isn't like other types of robustness that we often see in statistics where something like heavy tails or means are decisive, that in fact, what is going on is that it's detecting some notion of signal to noise in our problem. Okay, so that's where we're going to go with the rest of today's talk. Let's start by talking about when do we care about dropping these small data subsets. So first, a first observation here is that if I have a useful data analysis, it's got to be sensitive to some change in the data. And so I think, there's this unfortunate thing, and I'm sure that I am guilty of this as well, is that we often talk about sensitivity and robustness as though they're monoliths. But of course, they're really always shorthand. When we say sensitivity, we mean sensitivity to some particular type of change. And so really the question that we want to ask ourselves is not, is our data analysis sensitive to any change, but what types of sensitivity are concerning to us? And that's really going to vary by problem. And again, I want to emphasize today, I'm not going to be saying, hey, here's all of the tests that we should run on our data analyses. Certainly, I will not be exhaustive in any way. Rather, I'm going to say, hey, here's one type of sensitivity that often concerns us. And so that's the point that I want to make, that this is one kind of test that we should run on many data analyses. So in order to talk about why we might care about dropping very small data subsets, let's look at some examples from economics. Why economics? Well, one, it's hugely influential. It drives major policy decisions that affect all of our lives. Two, man, it is a fantastically reproducible field, as we're going to see in my examples today. And prosaically, we were lucky enough to collaborate with just a wonderful economics expert in Rachel Meager. Okay, so why do we care about dropping very small data subsets? Well, here's an example. An issue that arises just about all the time in statistics and machine learning is that people use standard tools, and those tools report something that isn't necessarily exactly what they care about. So for instance, suppose that we're interested in the effect of microcredit. Well, a really common situation is that there are a bunch of villages, and we will randomly assign some villages to receive microcredit and randomly assign some villages not to receive microcredit. And so in real life, what people will really do is look at the average business profit of the small businesses that received microcredit and say, how does this compare to the average business profit of the small businesses that did not receive microcredit? Now, what we actually care about is, did microcredit help many people get out of poverty? But what we're measuring is an average profit. And so if, for instance, one of the richest people in the world, Jeff Bezos, just happened to walk into one of the microcredit villages before we measured business profit, the business profit of people in the microcredit villages would be through the roof. It would be incredible. And we would say, oh, wow, the average business profit is so much higher in the villages that receive microcredit. This is looking really amazing. Microcredit's really helping people. We would like to know, though, if there was this one really weird data point. If I could remove Jeff Bezos from my data and see that the results would completely change, which they would in this particular case. Not only do we have this issue of reporting a convenient proxy in general, but it's always going to be the case, as we said at the beginning, that our policy population is different from the analyzed population. So, we run a microcredit study in Mexico in order to understand something fundamental about microcredit. But the reality is that if we have some kind of public policy, it's going to be applied potentially in an entirely different country than Mexico. It's going to be applied in a potentially different set of villages than Mexico. It's definitely going to be applied at a different time than the original analysis was run. And so we might be concerned if our results hinged on an extremely small proportion of our data, because that was maybe just specific to that original analyzed population. Something that is definitely the case in the social sciences in general is that small fractions of data are often missing, not at random. Maybe we have some kind of survey and we follow up with people on the phone, and some people don't have phones. There's always issues of things like non-response bias. And so just in general, we have this issue that we could depend on a very small amount of data. And so if that were the case, and we just happen to include it or not, we'd worry about the generalizability of our conclusions. And of course, we know that in statistics, our models are just necessarily misspecified, unless you're in maybe some very specific area of physics. Certainly in the social sciences, there's no way that our models are capturing the rich things that are going on in real life. And so they might be useful nonetheless, but we would worry if they were, really depending, our results were really depending on a very small subset of our data. So hopefully you feel at this point that there are many cases where we would be concerned if dropping a very small fraction of our original data changed our substantive conclusions of an analysis, like whether microcredit helps people or hurts people. Now, I want to emphasize these concerns are very much not specific to economics. I've been talking about economics because it's a nice set of examples, but absolutely in just about every area, we're reporting a convenient proxy because that's what our statistical tools handle, our standard tools. but not necessarily because it's what we fundamentally care about. The ways that we want to learn in science and engineering are fundamental. We want to be able to apply universal principles in the future. And of course, our models are just necessarily misspecified in general. Okay, I also want to emphasize that it is not the case that in absolutely every data analysis, you care about dropping small data subsets. So for instance, suppose that you're studying crime in two cities. Hopefully there is an extremely small proportion of murders in both cities. And so maybe in one city with 100,000 people, there are 10 murders, and in another city with 90,000 people, there are 5 murders, and maybe you want to do some sort of comparison. In this case, definitely dropping a very small fraction of your data will get rid of all of the important and interesting data. But also, on the other hand, you should be really clear that if you're doing a comparison study of murders, your data size might effectively be seen as 5 versus 10, not tens of thousands or hundreds of thousands. So hopefully at this point we care if dropping an extremely small fraction of our data would change our substantive conclusions. And so let's talk about what that might look like in practice. So in particular, I might worry if removing a very small fraction of data changes my conclusions. So let's start adding some notation and ways of talking about this to our discussion. So let's say alpha is our fraction of data that we're concerned about. So in particular, we'll say that alpha is some value between 0 and 1 because it's a fraction. But in general, we're going to be thinking of alpha as being a very, very, very small value, ideally near 0. What does it mean to change our substantive conclusions? Well, it depends on the statistical analysis, but some really common ways that we make decisions in statistics are we look at the sign of some effect, like the effect of microcredit. Is it positive or is it negative? Maybe we decide to invest in microcredit if it's positive. We might look at the statistical significance of an effect. Is it statistically significant? Is the effect of microcredit statistically significant? And very commonly, we'll look at both the sign and the statistical significance. So maybe we'll invest in microcredit if it has a positive effect and that is statistically significant. So now that we have this conception of what we're trying to do with our study, let's define what we're going to call the maximum influence perturbation. What's the largest possible change that we can make by dropping at most 100 alpha% of our data? So for instance, if I'm concerned about dropping some small fraction alpha of my data, I want to know, is it going to change my conclusion? I might ask something like, how much could I change my effect size by dropping alpha fraction of my data? And then I could ask, was it enough to have changed, say, the sign of the effect, if that's what I cared about? Now, once I've identified that, say there's some super small part of my data that I could drop it and change my conclusion, I probably want to know what those data points are. And so we're going to call this the most influential set. What data can I drop to achieve this maximum influence perturbation? So for instance, again, if like Jeff Bezos walked into my microcredit villages, my randomized controlled trial, I would want to know, hey, who is this data point that's totally changing my analysis? And so he would comprise my most influential set. Another way to consider this, to think about this, is what we're going to call a perturbation-inducing proportion. This is the minimum data proportion that is necessary to achieve a certain change. So for instance, suppose that, again, I'm concerned about changing the sign of an effect. That's how I'm making my decisions based on the sign of an effect in my analysis. Then I might ask myself, how much data do I need to drop to change the sign of the effect? If it's very, very, very small, I'm concerned. If it's larger, like on the order of even, 4% or 5% of my data, I might stop being as concerned because eventually I'm going to change enough of my data that I can change my analysis. So then our question becomes, how can I calculate these quantities? So in particular, for instance, how could I find this maximum influence perturbation? Well, here's an idea. I could just rerun my data analysis with every small fraction drop. Certainly, this is conceptually straightforward, and it should achieve the goal of finding, is there a small fraction of my data that I can drop that would change my conclusions? The problem is that it's not very feasible in practice. So let's start with a very small example, and then we'll get to a somewhat moderately sized example. Suppose I had just 400 data points, And I was concerned if my conclusions would change if I dropped 1% of my data. Well, that means I want to see, would my conclusions change if I dropped any 4 data points, if I dropped any 3 data points, if I dropped any 2 data points, or if I dropped 1 data point. So let's suppose for the moment that all I have to check is every 4 data points. Well, that's still 400 choose 4 data analyses, or 1 billion times, over 1 billion times that I have to rerun my data analysis. So if my original data analysis takes just 1 second to run, which if you run any data analyses, you know that that could be pretty optimistic, this check would still take over 31 years to run. Now consider a slightly larger problem. Suppose I have 16,000 data points. And let's make this even easier. Suppose I only care if my analysis changes if I drop 0.1% of my data, a very small fraction of my data. Well, in this case, I'd have to rerun my analysis over 10 to the 53 times to check if there's that very small fraction of the data I could drop to change my conclusions. If each analysis takes 1 second to run, this check would take over 10 to the 46 years. I think a lot of times nowadays in machine learning and statistics, you sometimes hear people say, hey, let's just take advantage of distributed computing. And this is a case where distributed computing is just not going to save us. We could have all of the compute power of Google as a company, and we still wouldn't be able to solve this sort of simple, 16,000 data point problem. So this is just a combinatorially way too expensive problem. And so we're going to need some kind of approximation to deal with it. So we provide an approximation, but before I get into the details of that approximation, I'd like to show you it actually working in practice. So let's look at an actual microcredit study. So Angelucci et al. 2015 was the largest of 7 very famous randomized controlled trials in economics that all examined the effect of microcredit. So there were over 16,500 households in this Angelucci et al. 2015 study. I cannot emphasize enough the fantastic reproducibility and data sharing of this paper in particular and economics in general. It's really amazing. The original model here is very straightforward. Let's look at the simplest version here. We have a simple linear model. Little n, the index little n, indexes the household or the small business. Xn tells us in the randomized controlled trial, we observed, did this household receive microcredit or not? And then Yn is the profit of the associated small business, which we also observed. And then finally, we have these 2 parameters, theta naught and theta 1. So theta naught is essentially what is sort of the average business profit without microcredit. And theta 1 is the effect of microcredit. How much is microcredit helping if it's positive or hurting if theta 1 is negative? Now, my understanding is that economists also did much more complex models with tons more covariates describing the small businesses. And it turns out that basically you get kind of the same results in either case. And so we're just going to focus on this super simple model. In the original analysis, and we found exactly the same thing, theta hat 1, or theta 1 hat, is negative 4.55 US dollars purchasing power parity for every 2 weeks with a standard error of 5.88. And so on one hand, this is looking not so great. Microcredit is actually having a negative effect in this case. But on the other hand, it's not a statistically significant effect because we're within a standard error. So if we want to ask, would this result change if we dropped a very small proportion of data? Well, we can use our approximation, which luckily does not take 10 to the 46 years. As we just talked about, it takes just 2 seconds to run. So it is a lot more reasonable. It's something that people can actually run in practice. We find that we can remove 1 household from 16,000 and change the sign of the effect from negative to positive. Now, you're probably thinking to yourself, yeah, but it wasn't statistically significant to begin with. So do I really, am I really bothered by that? Here's, I think, the more compelling point. We can remove 15 data points from the original analysis and change to a statistically significant effect of the opposite sign, a positive effect. So this is something where we would really be changing the substantive conclusions of the analysis and the things that we would actually do, the decisions that we would make based on this analysis. Now, a couple of points about this. One, you can rerun this regression to check directly. So, you could very reasonably be worried that, hey, we made this approximation. Do you trust the approximation? Is it really telling you what's going on? But remember, we tell you the problematic data points. We say, here are the 15 data points that if you drop them, you would get this change. And so then at the cost of just one extra analysis, not 10 to the 50 analyses, you can just rerun the regression without those data points. And in fact, we verified here that we get the same results as via our approximation. Two, I think very reasonably, you might be thinking, yeah, but it wasn't statistically significant to begin with. And so, maybe I didn't really trust this result to begin with. We're going to see an example later where you can start with a statistically significant result in a very famous study, and we can still drop a very small fraction of data to get statistical non-significance. We're going to see later examples where people trimmed gross outliers in advance, and you can still be sensitive. So it's not just about gross outliers. We're going to see examples later where you can have light tails or be reporting means, and that's not decisive, that you can be either non-robust or robust. And the same thing happens with Bayesian inference. So we go into this in detail in the paper with some real life examples using Bayesian inference, that you can be either robust or non-robust, that Bayes isn't a panacea in this case. So we've seen the approximation in practice now. We've seen that we can actually detect non-robustness. We're going to see more examples of this. But now hopefully we're interested in learning about what is this approximation. Oh, and we're going to see later that the issue that this is picking up is some notion of signal to noise. Okay, so far we've talked about when do we care about dropping small subsets of our data. We talked about how we would like to drop these data subsets if we had infinite computational power. We talked about why it's so computationally expensive. And now we have this fast and automatic approximation, so we don't have to deal with that expense. And so that's what I'm going to go into in detail next. So let's look at a pretty generic data analysis to set this up. So suppose I have a data point, let's call it DN. And in general, I have, capital N of these data points. Now, these could take a lot of different forms. One example would be if I have a set of covariates, let's call them XN, and a response, YN. But it doesn't have to be a kind of supervised learning problem. This could be semi-supervised learning. This could be unsupervised learning. These are all acceptable. Now, typically I'll have my parameters, my unknowns that I'm interested in learning about. Let's call them theta. And I might have some loss that relates my parameters to my data point. Now, a very typical setup for a data analysis would be that I sum up my loss over my capital N data points, and I minimize that loss to get my estimator, let's call it theta hat. Now, what I've described already, describes a lot of data analyses that we might do in real life. So anything that has the form of minimizing the loss, if we're doing maximum likelihood, all the F's could be negative log likelihoods. But I want to point out that our actual approach handles even more general data analyses. So for instance, if you are being Bayesian, this can handle a variational Bayesian approximation. It can handle a penalty, whether you're Bayesian or not, or interpret that as a prior. So you can handle MAP, but also just generally penalized, minimizing a loss. You can handle multi-step analyses where you have some kind of minimization and then another one. Basically anything in the form of a Z estimator. But the data analysis I've written here is already pretty general, and I think it'll be illustrative. So I'm just going to stick with this particular notation for the talk. Okay, now typically we don't just end there. We actually have to make our decision based on this data analysis. And so let's call our quantity of interest that we use to make our decision phi. So for example, when we were talking about the microcredit data analysis a moment ago, the parameter vector was theta 1 and theta naught, but we actually just used theta 1 to make our decision. And so phi could be just a particular element of that parameter vector, maybe the pth element of the parameter vector. Or maybe if I'm trying to make a decision based on statistical significance, phi could be the pth element of the parameter vector plus or minus 2 standard errors. Okay, so everything above this bullet point is sort of, just a statistics review. This is pretty standard fare. But now I'm going to start thinking about this problem just a little bit differently. So in particular, we're going to imagine that we have weights on all of our data points. Let's say data point 1 gets a weight of size W1, data point 2 gets a weight of size W2, data point 3 gets a weight of size W3, and so on. And you can think of our original problem as assigning all of these weights a weight of size 1. So W1 equals 1, W2 equals 1, W3 equals 1, et cetera. We can collect those ones in the all ones vector. Let's call it 1 sub capital N for N data points. And that's our original problem. And a way to conceptualize dropping a data point is that we take its corresponding weight from 1 to 0. So if we drop the 10th data point, we take W10 from 1 to 0. If we drop 2 data points, we take both of their weights, say, from 1 to 0. And so on. And so hopefully you agree that every dropped data subset corresponds to a different weight vector W. Okay, so how does this change our data analysis up at the top? Well, let's look at our loss function. Essentially what we're going to do is we're going to take each loss and pre-multiply it by the corresponding weight. And so if Wn is 1, then I'm keeping the loss term for that data point. And if Wn is 0, then I'm getting rid of the loss term for that data point. So now implicitly theta hat is going to be a function of W. And so in turn, phi is going to be a function of W. For 1, just because it's a function of theta hat, which is a function of W, but also phi might be a function of W, the weight vector, via something like the standard error. So not just via theta hat. So at this point, we observe that phi, this quantity of interest, the thing that we're using to make our decisions, is a function of this weight vector W. We have to compute it, it seems, for every possible drop data subset. That's a ton of different W. That's way too expensive. So we don't want to do that. But let's also observe that every W that we care about, because we're dropping this very small fraction of data, every W that we care about is very, very close to the all ones vector. And so that's going to be our main observation here, is that we're only perturbing W a tiny bit from the all ones vector. Phi itself is a function of W, and so let's just use a Taylor expansion in W. And in fact, what's the simplest non-trivial Taylor expansion that we could use? It could be a first order Taylor expansion. And so that's going to be the whole idea of the approximation, is just a first order Taylor expansion in W. So here we have our generic looking data analysis up at the top. We take from that our quantity of interest phi, where we have an example of phi. And now I'm just going to write out this first order Taylor expansion around our original data analysis, which correspond to the all ones vector in W. Okay, so let me explain everything that's going on in this equation. On the far left-hand side, we have phi of W. This is the exact quantity that we wish we could compute for every W, which corresponds to every dropped data subset. But we can't, because it's way too expensive. We can't do this 10 to the 50 times. We can't run our data analysis 10 to the 50 times. And so instead, we're going to provide a linear approximation, which we'll call phi lin for linear. And as I said, that's going to be exactly a first order Taylor expansion. And so in particular, we have the 0th order term in the Taylor expansion. So that's just phi of the all ones vector. This is what we get from running our original data analysis. It's sort of a sunk cost. You have to run at least one data analysis. But now, to avoid running all of these other data analyses with the different W values, we're going to have a first order term in our Taylor expansion. This is effectively a dot product between the difference in weights between our weight vector and the all ones vector and a first derivative. So this is the first derivative of phi with respect to W. If you're familiar with influence functions, this probably looks pretty familiar. We're going to call this the influence score of the nth data point. If you're not familiar with influence functions, don't worry about it. The main question that we have about this derivative is it something we can compute? Because everything else in this equation is pretty straightforward. We get phi of 1 from our original data analysis. We get the difference in the weights in 1 just pretty trivially, but now we want to ask, can we compute this derivative? Okay, well, there's two parts here. First, we, and by we, I mean the authors of this paper, nobody else has to sit down and do any work. This should be really automatic. We can write a formula for this influence score using the implicit function theorem and the chain rule and reduce it to derivatives of things like f with respect to theta. Now, those derivatives, in turn, we can compute with modern automatic differentiation tools, which hopefully you're familiar with automatic differentiation. It's really revolutionized a lot of computing in both statistics and machine learning over the past decade. There's this fantastic survey, just in case you haven't seen it, by Baden et al. 2018, automatic differentiation in machine learning, and it gives you a real sense of how things have changed thanks to these tools. I think the most important thing is that these tools are now really easily available and baked into typical programming languages that we use in statistics and machine learning. And so there's no effort that has to be done on the part of the user. We get these really accurate derivatives for free, essentially. So this is something that we can compute in practice, that we can compute automatically, that people don't have to sit down and derive equations to use. We said that we wanted to get away from 10 to the 50 data analyses, and now we only have to run one data analysis, the original data analysis. So that's also as desired. As I said, this is just one particular sort of example of a data analysis, even though it's pretty general. We can have priors, we can have regularizers, we can have multi-stage analyses. That's totally fine. You might also be thinking to yourself, hey, why stop at the first order? I could totally do a higher order Taylor expansion. And yes, that's definitely true. And so in fact, we have in some very early work on the archive, which again, I just want to emphasize is pretty rough and early. We do believe that a higher order Taylor expansion can be useful for approximating something like the bootstrap, which can also be seen as a reweighting of the data that you have. But for our purposes today, it's actually really important that we're using a first order Taylor expansion. And that's because I haven't totally solved this problem yet. So far, what we've done is we reduced 10 to the 50 data analyses to one data analysis. But at the moment, it looks like I still have to compute my linear approximation for every weight vector W. And I don't want to do any computation 10 to the 50 times, even if it's just addition. It's still way too much. And so we're going to have to get away from that combinatorial explosion of computation. Now, in order to do that, we're going to make the observation that ultimately what we want at the end of the day is the biggest possible change. I'm going to assume at this particular time that we want change in a particular direction. If I wanted the other direction, I would just flip this around with the sign. So I want to know, what is the biggest possible change that I can achieve by dropping my small fraction of data? I'm using my approximation. I'm not going to use the phi's directly. So we're going to say, what is the biggest possible approximate change that I can get by dropping my very small fraction of data? And we can write this quantity by just using the Taylor series formula above. So here I'm just taking that phi of the all ones vector and bringing it on the other side. Now, when we look at this term, it really simplifies quite a lot because it's essentially just the sum over the cases where Wn is equal to 0 of the negative of the influence score. Because in the immediately previous formula, if Wn is equal to 1, well, I have 1 minus 1, that just goes away. And if Wn is equal to 0, I get a negative 1 term. Okay, so this suggests a general algorithm. The algorithm says, step 1, compute the influence scores. That's going to be a linear time operation in the number of data points. Step 2, sort the influence scores. Technically, this is an n log n operation, but if sort is the biggest bottleneck in your data analysis, you're probably doing pretty well. And then step 3, we're going to start removing the largest influence scores. So first, we're going to remove the absolutely biggest one to get the biggest change for one data point. Then we're going to move the second biggest one to get the biggest change from 2 data points, and so on. So let's recap. We wanted to compute the maximum influence perturbation. What is the largest possible change that we can get by dropping at most alpha fraction of our data? So now we're going to compute the approximate maximum influence perturbation. In particular, we'll remove the largest influence score, then we'll remove the second largest influence score, and we'll keep doing this until we've dropped at most 100 alpha % of our data, and then we'll ask what is the change that we got. In particular, what is the approximate change that we got? As we do that, we can say what are the data indices of the data points that we dropped, and those are our approximate most influential set. What are the data that we dropped to get the approximate maximum influence perturbation? Again, another way to look at this is we're interested in the minimum data proportion to achieve a certain change. So then what we can do is we can start by removing the largest influence score and ask, did we achieve that change? If not, we remove the second largest influence score and ask, now did we achieve that change? And we keep doing this until we achieved the change that we were concerned about, or we eventually remove all the data and we say, hey, we weren't able to achieve that change. And in all of these cases, we now have an n or n log n computational dependency. We don't have any kind of combinatorial dependency on the number of data points. So this is the exact approximation that I used in my example earlier, the microcredit example. And now we're going to spend a little bit more time seeing some intuition for it from a simulated example and some more real life data examples. So we're going to look at a simulated example first, because one, that lets us make sure that we completely control any notion of misspecification. And two, it lets us get a lot of intuition in a case that hopefully we have intuition about. And so we are going to look at just about the simplest model that you can look at that is still continuous and there's interesting things going on there. We're going to look at a linear model with Gaussian noise. Okay, so we have our one-dimensional linear model here. Xn, our covariate, our single covariate is just one-dimensional. Theta is one-dimensional, and Yn, our response, is one-dimensional. Now we have a noise here. We're going to be simulating from this model. So we're going to simulate exactly from this noise, and it will be controlled by a variance. Let's call it sigma squared epsilon. We are simulating our data. So we're going to simulate the Xn, and we're going to give them their own variance, sigma x squared. And again, we're simulating our data, so we're just going to choose theta to be -1. Now, in this simulated problem, we're going to decide that we are choosing our decision. We're making our decision in this problem based on the sign of theta hat. So we're going to draw 10,000 data points. We're going to act like we have a 10,000 data point data set, and we're going to ask, can we flip the sign of theta hat by dropping some of those 10,000 data points? Now, I said earlier on that what's really going to end up driving this AMIP, this approximate maximum influence perturbation that we have, this metric of dropping data that we have, is a notion of signal to noise. So what do I mean by signal to noise? Let me give at least just a little intuition for this problem, and then you can check out our paper for a much more precise notion. But in this problem, and in general, signal is sort of the strength of the effect. In particular, in this case, we're trying to change the sign. And so we have to make a change, or let's call it delta, of size theta hat in order to go from theta hat to 0, to change that sign. The intuition here roughly is that if theta hat is very large in magnitude, it's easier to detect its sign. If theta hat is very small in magnitude, it's easier to mistake its sign. Noise, conversely, is what makes this a hard problem. Roughly, how big of a change can you get? We show in the paper that our approximate maximum influence perturbation metric breaks down roughly as a shape term times a scale term. The shape term is pretty constant across different problems, and the scale term is an estimate of the scaled asymptotic standard deviation. For the purposes of intuition in this particular example, this is roughly sigma epsilon divided by sigma x. Let's think about why this makes sense. If sigma epsilon is very small and sigma x is very large, just think about the data that we would generate here. It's going to look like this perfect textbook line. It's going to be so obvious what theta is. There's going to be no question. Conversely, if sigma epsilon is very large and sigma x is very, very small, you're going to have a blob of data, and it's going to be totally unclear what theta really is. And so the conception here is that if signal to noise is very high, this is an easy problem. It's a very robust problem. It's very stable. Whereas signal to noise is low, this is a very hard problem. It's a very non-robust problem. It's very unstable. Okay, well, let's see this borne out in practice. So what we're doing here on the horizontal axis is we're increasing sigma x. We should be making this an easier problem by increasing sigma x. On the vertical axis, we're increasing sigma epsilon. We should be making this a harder problem by increasing sigma epsilon. Now, for every one of these little blocks, we have our 10,000 data points, and we ask, using our method, are we able to remove some proportion of that data to change the sign of the effect? And we find that when sigma x is very large and sigma epsilon is very small, the result is super stable. We actually can't find enough data to remove to change the sign. Now, as sigma x decreases and sigma epsilon increases, we're eventually able to remove some data along this diagonal to change the sign, but it's a lot of data. We have to remove a lot of the original data to change the sign. Finally, though, when sigma epsilon is very large and sigma x is very small, we could remove a very tiny fraction of our data and change the sign of the effect. And we see a very similar sort of motif when we try to change, instead of the sign and the statistical significance, or if we try to change the statistical significance. Now, in all of these cases, what we are seeing is that what this notion of dropping a very small proportion of data is picking up is a low signal to noise ratio. If signal to noise is very high, if this is a really straightforward, clear problem, we can't drop a very small proportion of data to change the analysis. If signal to noise is very low, this is a very unclear problem, we're able to drop a very small proportion of data to change the analysis. On the other hand, we're seeing a lot of things that are not decisive. Misspecification is not decisive. As we said in the beginning, it might be something that worries us, but it's not the issue on its own. Here we're seeing a case where everything is perfectly specified, and yet we can still drop a very small proportion of data and change our analysis in some cases. We can see cases that are not misspecified that are either robust or non-robust. Same thing with means and heavy tails. This is an example where we are estimating fundamentally something that looks like a mean. We do not have heavy tails, but neither one of these things is decisive, unlike in some other types of robustness. We're seeing examples that are both non-robust and robust in either case. Let's look at some real-life data analyses. So there's this very famous Oregon Medicaid study. We're going to see here that a small p-value is not decisive. So in particular, we're going to be reproducing this very famous paper by Finkelstein et al. 2012. Again, I just can't emphasize how awesome the reproducibility is in economics, and I think how much we could all really, really stand to learn from this field. Okay, so very famously, there was a lottery in the United States state of Oregon, and the winners were able to sign up for Medicaid, for healthcare coverage. And so this offered a natural experiment for understanding the effect of Medicaid on health, but also economists look in this paper at just the effect of the lottery on health. So there's a lot in the paper. I'm just going to look at one particular result here. And we also look at all of the other results in our actual paper. So one notion of health, and again, there are many different notions of health in the paper, but one notion of health that they look at is after 1 year, what is the number of days of no impaired activity over the past 30 days? In this case, the original paper has over 21,000 data points. This is a pretty humongous data set. Especially for this kind of thing, this is pretty substantial. And they found P was less than 0.01 for a positive effect. It's a very sort of exciting P-value to find in a study. But we do find in this case that you can drop just 11 data points and change the significance, the statistical significance of the result. Now, I do want to point out that this isn't 5% of the data. It's not 0.5% of the data. It's 0.05% of the data. So it's a very, very small fraction of the data. Let's look at another very famous study on cash transfers. We're going to see that this metric can return robustness. We saw this in some simulated data. You know, there's a bias in giving a talk or in giving a paper that I want to show you that, yeah, we can detect interesting non-robustness. But let me also show you that we can find that methods we don't always find non-robustness. We're also going to see that removing outliers isn't a panacea. So here we're looking at this Angelucci and DeGiorgi study from 2009. Again, just really awesomely reproducible. They looked at two different things in this study. So the first was the direct effect of cash transfers for poor households on household consumption. And the second one is this really interesting idea of a spillover effect. So the idea is, hey, if poor households in your village receive microcredit, do the non-poor households who did not receive microcredit also benefit? Okay, so let's look at both of these separately. So first, let's look at poor households. There were over 10,000 data points in the poor households part of the study. And we find that you just have to drop a lot of the data to change your analysis. So the reason that I have a range here is that we looked at changing the sign of the data analysis. We looked at changing the significance of the effect. We looked at changing the sign and the significance. And they all took a lot of data, you know, at least over 4%, if not 10% of the data being dropped to change the analysis. And so this seems like we can't conclude the kind of non-robustness that we can when we drop 0.1% of the data or some very small amount and change the analysis. Now, conversely, we can look at the spillover analysis. There were still over 4,000 data points here. And we find, first of all, let's just note that the original analysis actually did some pruning of outliers, some trimming of outliers to start. So they deleted households with consumption greater than 10,000 units. But we find that the analysis, even after this trimming, is still sensitive. In particular, we can drop just 3 data points, that's less than 0.1% of the data, to change the statistical significance of the analysis. And you know, we might ask, like, how could this be? And what's nice about linear regression is that, again, we have a lot of intuition. And so we can think about what's going on there. And in that case, we can, you know, check that the influence score isn't just the residual, it's the residual times the leverage. And so you can imagine trimming based on something like the residual, but then you could still have something that has maybe a moderate residual and a moderate leverage that together combine to be a large influence score. Let me just quickly run through some connections and then I'll conclude. So I want to emphasize that, you know, we've looked at economics here, but these concerns are very much not specific to economics. If anything, I think they have this amazing reproducibility that makes us like totally able to look at the analyses they're doing. Unless we have that reproducibility, it's hard to even look at other areas. And so that's, you know, even step one. But also, this just isn't something people reasonably could have run in the past. As we saw, it was just incredibly computationally expensive. It wasn't feasible. And so hopefully now it can be a useful tool going forward. I want to emphasize that our approximation is local. You trust it insofar, or you trust its quality insofar as you trust the Taylor expansion. Now, as we said, it is any non-robustness it finds is conclusive because you can do this check directly afterwards. But it's possible that if the Taylor expansion failed, that there could be some additional non-robustness that we're not picking up. And so if you can run some kind of global check, that's really great. I'll also just mention that we come from sort of a line of local robustness, other types of results that we've really built on from previous years. This is complementary to other types of robustness. So another very common type of robustness that people are interested in data analysis is this idea that somebody could come in and arbitrarily change some of your data points. Now, if you have an adversary who could really change your data points, that's something you should legitimately be concerned about. In other cases, it's not so much that we have an adversary who's going to change our data points. We just have this concern about generalizability that I talked about today. And so, of course, people have also done robustification procedures in other areas, and so that's complementary to our concerns today. We also come, in some sense, from a growing literature on using influence functions for practical checks. And so one area that this has been big recently is in approximating cross-validation. We have some work in this area, which we have also extended to high dimensions and to structured models. So you'll notice that the work I talked about today, if you see that loss function that I presented, it's sort of this sum over a bunch of losses for the individual data points. You could think of that as if we were doing maximum likelihood, looking like an independence assumption. We might want to get away from that, and we do that in this work that I'm showing here. And finally, I'll just say that, like many things that I think we're doing nowadays, ultimately, some really cool ideas that we're building on were really from much earlier in statistics. And so in this case, we're really building on ideas from the 70s and 80s in statistics. So there's this beautiful set of ideas called the infinitesimal jackknife from the 70s and 80s that's basically very, very similar to what I talked about today. And at the time, it was a theoretical tool. It was this thing that you could use to prove things like asymptotic normality and consistency. And it wasn't considered feasible that you would sit down and write out derivatives. And now we have modern automatic differentiation tools that are just built into our software, the software that we tend to use in statistics. And so it's just taking really these old ideas and making them practical and easy to use. So today I talked about a way to check if there is a very small fraction of your data that you can drop to change the decisions that you're making with a data analysis. I hope that people will check this out and try it out in their own data analyses and see what are those data points if they exist. So our paper is up on the archive. I hope that you will be interested enough to check it out and to read it. You can check out our code at the following repo. So I want to emphasize again my amazing postdoc, Ryan Giordano. So R Giordano is for Ryan Giordano, and ZAM influence is for Z estimator maximum influence. If you're interested in the phenomenon of p hacking, which is increasingly an issue in various data analyses, you'll note there's this great blog post by somebody who is not us. Michael Weave has this great blog post up about how our AMIP metric can be used to flag p hacking. And Ryan Giordano, again, my excellent postdoc, has a follow-up blog post that I think is also super interesting. And then finally, again, just reiterate this point that our check is meant to be part of a data analysis ecosystem. It's meant to be part of hopefully many checks that you run on your data analysis. I definitely want to emphasize that I don't think that there's any kind of a gotcha for economics here, that we've certainly dealt with other areas where there's less reproducibility, and I think a lot of room for growth there. So we have this paper, Transparency and Reproducibility in Artificial Intelligence, looking at cases in the medical field where sometimes, or AI in the medical field, where sometimes we don't even have enough information written to fully reproduce the code, much less code even already available and data already available. And we also have this paper up, Prototaxonomy of Trust for Probabilistic Machine Learning, where we point out, again, what is this trust ecosystem look like? That somehow step one is, just even making sure you can reproduce these analyses. Now we're looking at a sort of step two. If I have a particular set of training data that I look at, how does that relate to my ultimate generalizability to being able to talk about, what are my decisions on future data? What are my conclusions on future data? And all the different ways that trust can break down, but also that we can build trust in our data analyses. Thank you so much. And thanks for having me out remotely. And thanks to everybody who's been listening either remotely or in person. I really appreciate it.